And we're live.
Hi everyone, welcome to SciPy India 2020. This is the first time we're doing an online conference. We didn't want to miss out on conducting SciPy India since we've done this for 11 years in the past. I'm really pleased to be welcoming Professor Sergio Ray, who I've had the pleasure of chairing SciPy US with. So I have gotten to know him very well. And he's an expert in geostatistical analysis. Is that an accurate description, Serge?
Close, yep.
Okay, and he's given many tutorials, and he's also very, very well published. So it's really a pleasure to have him. I will formally introduce him tomorrow. He's also our keynote speaker, and he's kindly agreed to give us a tutorial on PySal, of which he's a lead developer. So in the tradition of not keeping anything formal in our tutorial sessions, I will not take too much time. I just want to welcome you all to this conference and thank you for being with us. This is the first time we're doing this, so please, if you have any issues, bear with us. Let us know. We are available on chat, both on this Hopin platform as well as on the chat.scipy.in. Again, we will go through a formal round of introductions. We will introduce you to the platform and things like that tomorrow morning as well. But right now, we will start with the workshops. And once again, thank you so much for spending your valuable time with us, Serge, and joining us for SciPy India and kicking it off. Yeah, welcome. And welcome virtually to India. That's the best we're going to do this year. So, yeah.
Well, it's wonderful to be in India virtually. I can't wait to be there for real. Hello from California. It's 7:30 p.m. here. So interesting time difference. I think I'll share screen and get us oriented if that works.
I'll get off and hand it off to you, and yeah, I will be around. Thanks again.
And I'm going to make this big, so we'll spend a couple minutes to make sure you guys can see things okay and that the screen resolutions are. So probably, or I could just yell in and initially and let me know, because now I'm at full screen, so I can't see the chat.
So we will hang around on here and share our audio, and we will, if you have anything to say, we will tell you directly.
Okay, great. So just a little bit of background of what PySal is before we get started with the actual tutorial. It's the Python spatial analysis library. It began probably about 2005, a long time ago, and it was a collaboration between myself and my colleague Luke Anslin, who's at the University of Chicago. At the time, we were both working in areas of spatial analysis in the social sciences, so economics, sociology, political science, urban planning, and primarily developing methods where spatial dependence and are important to the study of all kinds of socioeconomic processes. And at the time, there was nothing in Python that would allow us to do the kind of statistical analysis that we wanted to do. We had to use languages like Gauss to estimate regression models with spatial effects, and that was pretty painful. But I stumbled into Python as sort of a serendipitously using it for just to learn Python, but quickly, this was back in the days of numeric, before NumPy, that it was really expressive way to formulate models that we needed to implement. So I told my colleague Luke, who's a electrician, he's sort of like the father of the field, and he also right away took to it. So we started using Python for our own research purposes, and it made us much, much more productive. And we wrote a couple papers that we used our own code to generate new types of models, new types of statistical estimation methods. And then people asked if they could use the code, and which initially struck horror into our souls, because at that academicians, not software developers, and it was not common at that point in time to share code. But it introduced me to the whole open source ethos. So it took off from there was not ever any plan. It was mostly like many open source projects scratching our own itches. But because of the network effect, it took off way beyond what we've ever expected, to the point now where we have a team of about 20 developers all over the globe. Many of these are former students who are now professors at different universities. And we're fortunate that it's a pretty cohesive group and very collegial, fun group to be part of. And now it's widely used beyond just the social sciences. So it gets used in all kinds of life and earth sciences as well. And it's been gratifying to see it take off.
So, sorry, I just wanted to point out that your screen size is a bit, as in it's very small to see the fonts. So could you just make the fonts a little bigger?
Yeah, let's try that. How is that?
Yeah, that's better. But if you could make it just one more size larger, that would be really nice. Yes.
How are we doing? That's good?
Yeah, that seems better. I'll let you know if someone tells me otherwise.
Excellent.
Thanks.
Something that sorry to interrupt, something that also helps is if you switch off your video, the screen size that is shared increases a little for the viewer.
Okay.
So you can do that once you start coding and stuff. So it's okay.
Yeah, I can do it now because you hear me. I just have to go to that window. So turn off my video. Is that better?
Yes. So if you turn off the video, the platform focuses only on your screen. That's what he's trying to say. Yeah.
Okay.
So yeah. So whenever you want to step in and you want to say something, turn it back on, and that's perfectly fine. They will see you small, and your screen will become slightly smaller.
Okay, but they can still hear me now?
Yes, everyone can hear us right now. Yeah, perfect.
Great.
Thank you.
Okay, so to date, PySal is about 18 different sub-packages or packages that deal with a particular part of spatial analysis, broadly construed. So we've organized it into basically 4 layers. At the bottom is what we call lib, and this is a set of packages, and we're going to explore most, but not all of these today. The lib layer has routines for reading and writing different geospatial formats. There's a rich variety of file types as data models for geospatial data. So it's important to be able to read and write those, and we spend a lot of time doing that. Spatial weights matrices are critical to many spatial analyses because they allow us to express in a formal sense the notion of what observations are geographically close to or should be considered neighbors of other observations in the data set. And we will spend some time on the weights today. You can think about the weights as expressing like a network or graph representation where you have an edge that connects that you want to consider as neighbors. There's also several routines for different aspects of computational things like Voronoi diagrams, alpha shapes, convex hulls that we need to implement different types of statistical tests. So when we started PySal, none of this really existed. So we wrote our own readers for these geospatial formats. This was before things like geopandas and Shapely came on the scenes. And we didn't want to do that, write these file routines in order to get to the parts where we wanted to focus our energy in, and that was in the exploratory spatial data modules and the model visualization. Now, because we have libraries like Shapely, Fiona, Raster.io, we're in a process of replacing our old we wrote with these new more efficient and performant components to the library. And that's opened up a lot of interactions between the packages. So it's a really exciting time to be part of the spatial ecosystem in Python. It's fantastic. So that's lib. And then at the explore layer, these are methods for what's known as exploratory spatial data analysis, primarily testing whether a map pattern, let's say you're looking at a map of crime rates, or a map of disease rates is very timely right now, and you want to test whether that map is random or if there's some spatial structure to the map. And there's many, many different ways to do that. We're going to explore some of those today in the workshop. But then there's another critical core of the exploration is when you have longitudinal spatial data, when you have maps over multiple time periods, and you're interested in whether the pattern is evolving in certain ways, and what is the role of spatial dependence in how the distribution, the attribute distribution, changes or not over time. And these are exploratory because you're investigating, trying to detect. You don't necessarily have a formal hypothesis that you want to test. That's higher up in the stack where we get to the model layer here. The econometric or regression models of different forms that treat the characteristics of spatial data more comprehensively than spatial methods. So if you want to allow for spatial interactions between your observations, that complicates the statistical analysis and doing inference be valid, parameter estimation, prediction, interpolation. That's what's in the model layer of the library. There's a visualization layer that allows PySal to interact with the ever-expanding visualization stack in Python, which every year at SciPy there's a new kid on the block in terms of visualization. So rather than us writing our own, we're trying to plug our API into these toolkits like matplotlib, Seaborn, Altair, and I'm probably missing some. And we'll do some visualization today. So that's an overview of the library, a little bit about the workshop, what I have planned today. We'll cover, make this bigger, geoprocessing, a couple notebooks on reading spatial data and then deriving new types of variables from spatial relationships. We'll do some geovisualization. We'll explore this in terms of the different types of spatial weights you can use and why you would want to use one type over another. And then hopefully some interesting cases of actually applying them to look at the question of disparities in housing values in Southern California. And then the literature, well, not the literature, the ESDA module where we're testing for hotspots and cold spots on a map, be it disease rates, innovation rates, economic growth, economic decline, pockets on the map that are significantly interdependent with one another, and how do we identify them? That's all about spatial autocorrelation analysis. There is a binder for the workshop. If you did all the materials on your own laptop or own desktop, you can play along by launch. Boot up quick because I think I tested it about 2 hours ago and the image was already built. So feel free to play along with that if you're comfortable with the binder. If you clone the repo and set it up, then you can play along as we'll go through these notebooks. So we have a total of 4 notebooks that are what I'm hoping we get through, but I added a couple more in case we go faster than normal. And if we don't get to those, they'll be there for extra credit if you want to explore those. The font size for the viewers. Is this okay?
A bit bigger.
Sure. Yeah, I'm going to close the file browser here. We're going to go through the notebooks. They're numbered 00 through 0. Going through those sequentially in case someone gets lost. Just yell out. We'll go back. Okay. So we're going to start with geoprocessing.
So maybe just one size bigger, please.
Okay. Good. And let me see if I can steal some screen.
Yes, better. That's better. Thank you.
Okay. So at the beginning of any spatial analysis, you have to get the data into memory, or you have to open the files and read parts of them. And one of the challenges for people who work with spatial data is there's an incredible variety of formats that are possible, even for the same kind of data model. So the conventional breakdown is between so-called vector and raster data models, where vector, you have discrete polygons or points or edges and nodes on a network. These are objects. You can think about it as an object model. In the raster world, you think of the geospatial reality as a surface. So you have phenomena that you're trying to model, be it, say, elevation or rainfall or temperature, where conceptually you should be able to measure because it's a continuous spatial process. But because of the pragmatic dimensions of data collection, you can't measure it everywhere. So you have sensors located in space, and you may generate data that tries to generate the surface. But the representation of that data is in pixels and rasters. Data models, and each of those have many, many, many different types of formats. Even if you're working with just vector data, there's many, many different formats. And even if you're working with raster data, there's many, many different formats. So there's a lot of data formats. And in this notebook, we're going to look at some of the more common ones that you interact with as, say, a social scientist. So a geographer, a human geographer, or an economist, or sociologist, or epidemiologist for that matter. We're going to work with geopackages, which are a more recent data structure, that file structure that's very nice, and the old legacy shape files, which have been around for a long time and are very painful to work with. We'll talk about coordinate reference systems. The thing we're standing on right now, or sitting on, is sort of a sphere. It's not quite a sphere, but it's not a flat two-dimensional plane, and that causes complications when we want to measure distances between places depending on our spatial scale. All right, so along the way, we're going to introduce other packages that we interact with, geopandas being a key one. That's helped us a huge amount in the PySal world, because, and we actually interact with geopandas quite a bit. We have developers who are both geopandas developers and PySal developers, and there's a lot of going back and forth between the packages. So we're going to start with some real data. We're going to read a geopackage for census tracts in Southern California. So census tracts in the US, for the United States government, the Bureau of the Census, which is responsible for running the census of the population every 10 years, census tracts are designed to hold about 4,000 people, and they're based on boundaries. So the census redraws these census tracts every 10 years and to try and keep them about 4,000 people. And then they record socioeconomic data on household size, housing values, poverty rates, age distribution. And this is their primary data source that social scientists in the US use. So we're going to look at census tracts in Southern California, which is about 9 counties in Southern California. So we're going to be looking at maybe about 20 million people in this data set. Okay. And a geopackage is a really nice format for geospatial information. It uses SQLite as the database, but it allows us to store heterogeneous data. So we can have vector data sets that are not just polygons, but we could also have layers for points and layers for the road network in the same geopackage. And that's a clear advantage over the old shapefile, where you can only have one layer type in the shapefile. And if you wanted to integrate, say, a road network with census tracts and point data, you would have to deal with 3 different shapefiles. Well, the geopackage gets rid of that, so it's very, very nice. It also allows you to mix raster and vector data in the same file, so it's fantastic. We're going to use geopandas and make sure I have the kernel run. Okay, so I'm aliasing geopandas as GPD. And the data lives on, it came with the the files for the workshop. So the SCAG region stands for Southern California Association of Governments. We're going to read the geo package. And that puts it into what's known as a geopandas data frame. And most people who work with Python are familiar with pandas. So a data frame is the key data structure. If you're not familiar with pandas, you can think about a data frame as essentially like an Excel spreadsheet. You have records on the rows, and the columns are the attributes. If you're familiar with it, what it is, GeoPandas extends the pandas data frame to add an additional column in the data frame. And that column is a special column that has a default name called geometry. The other columns are the attributes. So in this data set, we have N is for the count, the number of Asian population under the age 15, the number of Black under 15, the number of Hispanic under 15. So there's many, many attributes, but there's also this last column called geometry, and that holds the geometries for whatever the vector unit is. In our case, it's going to be polygons. And we'll see a picture in a second, or a visualization in a second. I'm skipping over the Fiona because that's another package you can use to interface with geo packages. If our geo package had more than a single layer, you would have to tell the geo package, all right, I want to read in the tracts layer. But in our case, we only have one layer, so this is redundant, but I just want to make it explicit. If we had multiple layers, you have to specify which one you want. So we have the data frame we've created. If we look ahead of the data frame, so the beauty of GeoPandas is it gets everything in pandas. So we have these nice top 5 records of the data frame. The first record, that's the geo ID. So this is the encoding system in the US. 06 is that's California. 037 is the county code. I think that's Los Angeles. And then these are the more detailed tract codes. So this tells us what census tract code we are in. There are 58 people reported who are under the age of 15 and recorded as Asian, according to the US Census. There are no young Black people living in that census tract. There are 223 young Hispanic people living in that census tract. And so there's quite a few attributes in this data set, and we're going to look at them. The last column, this encodes the geometries. So the geometries for our census tracts are polygons. So it's, if you like geometry, and the polygon, the representation here are the X and Y coordinates for the points that connect an edge. And this is a sequence of consecutive points that draw the polygon boundary. Now, these are the coordinates, so these are longitude and latitude for the coordinates. So that's what's in the last column, the geometry column. Other than that, it's a regular pandas data frame, but that geometry column is the special part for us. Okay, so there are 4,580 census tracts in Southern California, and for each census tract, we have 194 variables or attributes. Okay, we saw that of those 194 attributes, the last one is the geometry. And if we peek at it, you can see some more of the coordinates. So the X, Y for the polygons. All right. We can plot it. GeoPandas has a built-in plotting method. So, and we're going to expand on this as we go along. So just gives you a very high-level overview. So we have longitude here, and these are in decimal degrees, and latitude here. And these are the counties in Southern California. So San Diego is down here. I'm right about here right now. Los Angeles is up here. Riverside County's here. This is San Bernardino County. And then up here, we get into Ventura and Santa Barbara. These are the Channel Islands. Okay. All right, so we're going to bring in another data set. Right now we have a data set for all the census tracts in Southern California. And you can see as you get to Los Angeles, the tracts get smaller and smaller. As you get to the eastern part of the region, the tracts are much bigger because the population density is much lower out in the desert. So this is desert, this part of the state. This is the Colorado River. And then to the right here would be Arizona. Okay, just to try and orient. So we're going to do an analysis that happens quite a bit. So you might be interested in disparities in access to mental health services. This is a big issue in the US. So you might be a public health epidemiologist and you want to look at the locations of health clinics, behavioral health clinics in a subset of this region. So this scientist, this behavioral scientist has information on the location of clinics, mental health clinics in a part of the data, in the part of the region, but it's a different data set. It comes from what's known as a shapefile, which encodes the business name or the clinic's name, its street address, what city it lives in, what zip code. So we're creating another data frame with geopandas. We're reading now a different geospatial data format, a shapefile. But we get a data frame, a geopandas data frame. And again, it's a data frame, so we can list out what's in there. We have the type of clinic it is, the name of the clinic, the doctor's office, or the practitioners, the street address, phone number, zip code, and then these are points. So a point on a map versus the polygons, which were the census tracts. We can plot these because they are a geopandas data frame. So when we plot them, we get the extent that rectangle contains all the points, but the points now have a different coordinate system. These are not longitude and latitude. These are not decimal degrees because longitude goes between -180 and positive 180 at the date line. And then latitude goes from 0 at the equator to 90 in the North Pole, -90 in the South Pole. These are clearly not latitude, longitude. So we're going to have to rectify things. What this researcher wants to do is combine these points and put them on the map of the census tracts and then start to ask questions about these clinics are located with respect to the spatial distribution of different ethnic groups or different income groups, and ask if there's disparities in who has access to these public health resources. In order to do that, we're going to have to wrangle these two different data sets. One is in latitude and longitude, one is in a different coordinate system. So we're going to have to fix that. Okay, so what do we have at this point? Are there questions? I'm going to rely on my host to forward the questions if they are.
You're good. No question.
Okay.
Yeah. Looking great.
Fantastic. All right, so just to take stock where we are, we have two data frames. One that has the behavioral clinics, and these points are only in Riverside County. So I am at, my job is at the University of California, Riverside. And I have plenty of colleagues, I'm in the School of Public Policy, who are interested in health disparities. So this is not a fake example. This is one I was helping one of my colleagues with. She was interested in this question of health disparities, and she was focusing on Riverside County and needed to couple those clinics with census data for the tracts. So first, what we're going to do is Riverside County is only one of those 9 or 8 counties. So we're going to extract. I don't need all the tracts for this study. What I need are the tracts that are just in Riverside County. So I'm going to, step 1 is extract the Riverside County's tracts out of those 4,500 tracts. And because geopandas is basically pandas with some spatial stuff in it, we can leverage all the SQL type queries that are built into pandas. So we could have done this spatially and said, draw a bounding box around the geometries for Riverside because it's almost a rectangular county, but we that wouldn't quite work on the western part of the county. But we could cheat in a sense and just know that, well, Riverside County is in California. California is 06, and Riverside County, any census tract in Riverside County is going to have this string at the beginning of its geo ID. So we can do a string match to get just the Riverside County records and create a smaller data frame, and then we can plot that. So now we only have the census tracts for Riverside County. We're just extracting them from the bigger data set. So job one's done there. Now we want to combine the clinics with the census tracts, because my colleague's interested in this question: how many clinics are in each census tract in Riverside County? Are the census tracts located close to the core populations of the cities in this county, or is there some discrepancy between where the clinics are? So to get at this, we're going to use what's known as a spatial join. And what a spatial join does is it creates a linkage between each point, each clinic, and the tract that it is contained within. All right. And once we know that, then we can ask the tracts, how many of the clinics do you contain? Or we can ask each clinic, in essence, which tract are you inside? And that's done with the S-join for spatial join method, which lives on the data frame, the geopandas data frame. So it's just like a table join you would do with databases, but now we're using a geometric predicate is one point inside a tract. So we're going to create a new data frame, clinic_tracts, calling from the geopandas data frame. I'm sorry, we're going to call geopandas the function spatial join, and we're going to pass in the two data frames. The clinics data frame, which has the points, and RC is the polygons for the tracts, and the operation is within. So this is a function in geopandas that should return a new data frame. But we see a warning. And the warning alerts us to the fact that we have a mismatch in the CRS, which is the coordinate reference system. This is the way that data sets encode where something is on the surface of the Earth. And there's many ways to do that. Latitude and longitude is one, but those are geospatial spherical coordinates. The format for our points were in meters. So these coordinates are basically, I think they're UTM coordinates. So this is the number of meters from a certain reference point going east to west. And this is the distance in meters from a certain reference point on the Earth's surface in meters going to the north. These are not decimal degrees. And so that's why geopandas is throwing this warning. And this is a problem because as far as what's going on under the hood here with Python, we're asking if this square contains this point, but they have two different coordinate systems, so it's not going to work. So we can find out what's the deal with the coordinate systems. And on any geopandas data frame, there's a CRS attribute. So the clinics tells us that this is measured in survey foot, so it wasn't meters, sorry. And it's in the North American datum, 1983, California Zone 6. This is a critical key. This is the European Petroleum Survey Group, which has standardized how to represent coordinate systems. So there's a website you can go to and type in that code, and it'll return this information. And this tells us what those numbers mean in the geometry column for the points. So they are in survey foot. The X coordinate is east, the Y coordinate is north. The area of use has this bounding box in longitude and latitude. And to get those coordinates, there was a map projection that went from the original geospatial coordinates, the geographical coordinates, to these feet. So this tells us where those numbers were generated from for the clinic. So the clinics have a unit of feet, while the tracts are in decimal degrees, so our spatial join won't work because they're two different systems. And indeed, when we asked what did we get, when we did our join, there were no matches, because you can test whether a point is inside a polygon only if they have the same coordinate system. So the join didn't find any containment. So we're going to fix this. And the fix is fairly straightforward. There's a method on the data frame to change its CRS. So we're going to change the county CRS, which is in latitude and longitude, to use the coordinate system from the clinics. So this is in English saying change the coordinates of the point data set to match that of the tracts. And I'm going to plot what happens. So you can see that the coordinate system changes for the census tracts. That's what we want, so that now both data frames will have the same units. And I'm going to save it and repeat our join. And now we see we're in business. Now we have tracts that do contain an address of one of the clinics. Okay, so the spatial join now worked, but we had to harmonize the coordinate reference systems. And we could have gone either way. You could change the coordinate reference system of the tracts to match the points, or change the coordinate reference of the points to match the tracts. It wouldn't matter as long as they're the same. The join would work. All right, so we're in business. Now we're going to use pandas to figure out, okay, how many clinics are in each tract.
So Serge, just to pause here, there was a question a couple of minutes ago.
Sure.
Sean Ray, he's asking, is this all including visualization? Or is there matplotlib being used? That is the question.
For the ugly maps we've seen so far, we're going to get to better maps in a minute. Geopandas is using matplotlib. So this is matplotlib and using the patches and polygons to plot this.
Perfect.
That's what Geopandas is using. Yeah. All right. So we can use group by and pandas to find out how many of these clinics were in each tract. So we're grouping by the geo ID of the tract, and we find out that some tracts had 2, some tracts had 1 clinic. There was one tract that had 7. So that works. I want to save that. Now I only have 16 tracts that had at least 1 clinic, but there were a lot of tracts in the region that don't have clinics. So we're going to have to build things back up. And I want to report zeros for the tracts that don't have any clinics, because again, my colleague's interested in this equity question. And at the end, we'll cut to the chase here. Okay, so at the end of this, my colleague has a new data frame that was the original census tract data frame, but now has a column that has the count of the number of clinics in that census tract. And she can then start to do some investigation of the correlates that relate, say, is there disparities in terms of if it's high Hispanic or high Black tract, are there fewer clinics in that tract or nearby to that tract? Those kinds of questions. All right, I'm not going to go through the exercises because it's a 2-hour workshop. We do these workshops quite a bit, and sometimes they're all day, sometimes they're 2 days. And in those, there are exercises that we break out and do them. There's also the solutions to the exercises available. You would uncomment the # and load and run that cell. It would load the solution, and then you run it and you get the answer, but you want to try it out on your own. All right, so that was a quick deep dive on pulling in 2 different data sets with different geometries. We had polygons and points. and they had different coordinate reference systems. We were able to harmonize the coordinate systems and do the spatial join to construct new data. And a lot of geoprocessing is doing exactly that. It's creating data from existing data. So in the parlance of machine learning, it's spatial feature engineering, if you think about it. You're building up new features based on other features. Okay, so that's our first notebook.
Serge, I have a sort of naive question here. So
Sure.
the spatial joins are essentially doing it's not just like a pandas join. It's actually merging them based on the spatial locations. Is that correct?
Exactly. Yeah. It's asking, I want to join the census tract to the clinic that it contains. You could go either way because it's this asymmetric relationship. So the census tract could contain a point, but the point could be within a census tract, and you could do the join either way depending on what you want to do. Do you want to attach the census tract information to the point?
Right.
Or do you want to attach the point information to the census tract?
Right. But when you, so that happens only when you do an S join, right?
Yes.
And if you just did a merge or just a join, that would not do a spatial operation. Is that correct?
Correct. Yeah, you could do the merge on the other attributes.
Okay, and that's just the standard pandas merge / join.
Exactly.
Okay.
Yeah.
Awesome. Okay, thank you.
All right. Okay, so we're switching to the geovisualization notebook, which is 01. And let me close this. All right, and the visualization's a massive area in general in scientific visualization, and geovisualization is also very large, and it's a fascinating area. And the ironic thing is when we started PySal, we did not intend to do any visualization because at the time there were existing packages that were good at visualization, and we wanted to work. We were working on the statistical, sort of the quantitative methods, and you would export the results of your analysis to one of these packages like ArcGIS at the time, or ArcView at the time, or QGIS, and then do your visualization there. But over time, people wanted fast visualization. When you're doing exploratory data analysis, you want to stick in the notebook, and you don't want to export to another tool to do the visualization and then come back. It's very inefficient. So we've been trying to build in visualization, but I want to preface this by saying that wasn't our original intention by design, but we've added a bunch of modules to the library to facilitate this. There's one key package in our ecosystem called matplotlib that's used for choropleth maps. So choropleth maps are maps where you have aerial units, say polygons, and you have some attribute, say COVID mortality rates, for example. Every day on the front of the New York Times, there's a map of the U.S. with this horrible map of fatality rates. And choropleth maps use a color typically or a hatching pattern to classify the value of that attribute across the polygons. So you can use dark hues for high values, or you could use a thick hatching for high values and a less dense hatching for low values, or a light hue for low values. So matplotlib, which is a package in PySal, supports many different types of classifiers. Now the job of the classifier is to decide for a choropleth map, you need to decide on how many classes you want. So if you have, say, 3,000 census tracts and you have a measurement for a variable across each of the census tracts, you want to discretize the values so you know what is high and what is low. How many classes do you want to use to break the data apart is the first question. And then say you want 5 classes, how do you decide where to draw the bins? So it's like the rules for doing histograms for an attribute, but here the binning is going to be used to construct the visualization. So we're going to use matplotlib, geopandas, matplotlib. There was a question about matplotlib. We're going to use that. And then a package called contextually, which is also part of PySal, which allows us to pull in map tiles for the base layers. We're pulling the same geo package, so it's the same tracts for Southern California. I'm going to change the coordinate reference system to web mercator. And the reason for doing that is some of the base maps, like when you use Google Maps or Mapbox or Stamen, they typically use that projection, web mercator. So we're going to reproject our data, the geometry, to be on that CRS. And then we'll plot the default. So we're taking out a variable here. We're going to look at median home value, and I'll come back and unpack this in a second. So we're looking at one attribute, which is housing values. So this is the median reported housing value in the census tract from 2010. So this data is 2010 census. And the default is in geopandas, when we do this, we're plotting a column, is to do a quintile map. So the breaks are quintiles for the housing prices or the housing values. And the default color ramp or color map is virides. So the lighter hues are higher values. The darker hues are low values. So these are US dollars. So to be in the first quintile of housing prices or median housing prices in the US, $272,000. If you're below that, you're in the first quintile. And you'll start to see spatial patterns right away. The upper quintile, the fifth quintile, $632,000 gets you into the top 20% of housing values. The maximum is $1 million. Now, these are the median values, right? This isn't the maximum housing value in Southern California, but it's the maximum median census tract value. All right, so that's the default visualization. There's some problems with it. Number one, I don't really like this color scheme for this kind of data. Number two, we start to see the boundaries of the polygons are getting in the way for the small census tracts. You see more boundary than you actually see the fill color. So let's go back up here. This is the plotting cell. We're using subplots from matplotlib. This is our figure size. So if you want to make it bigger, you would change that. Then we're calling the plot method on our data frame. So that's our data frame. We tell it, if we just did the plot like we did in the previous notebook, you would just get the polygons. There was no attribute being mapped. But here we say we want to map the column of the data frame called median home value. And we want to use quantiles, stick it on the matplotlib axis that was defined up here. We want the edge color to be white, and the edge color is the color of the boundary of the polygon. We want the legend, which gets drawn over here, and the line width is the width of the boundaries. So you can play around with those if you want to make this more aesthetically pleasing, and then show it. So that's a basic choropleth map. And geopandas under the hood is using the map classify from PySal to do the binning, because we have about 17 different classifiers in there that geopandas surfaces. So that's the first cut. This might not mean much to anybody who's not from Southern California. You might not be familiar with the geography of the place. So we're going to add in some context. And that's why the package is called contextually. I'm going to fill in missing values. There are some missing values in the data set. They had NA, so I'm going to replace them with the mean just so we can move forward. And we're essentially going to do the same plot, but now we're going to add another layer, which is the base map. And for this, you do need to have a network connection because it's going to go out and get a tile to do the web layer. So I'll show you what we get first, and then we'll go back. So this provides a base layer that has additional information to orient you. So you have this large city names, you have the road network. Okay, so I'm down here in San Diego. Los Angeles is up here. You can see how large these counties are. Riverside County is about 112 miles wide. San Bernardino County is this big county up here, and it's the largest county in the coterminous US. That county fits the entire state of Maryland inside of itself, so it's massive. But contextually, we'll get these base maps, these web tiles that are very useful because they give you context. Even if you're from Southern California, it might be difficult to understand where these polygons are. So that can be very useful. All right, I'm going to pull out the housing values and do a little exploration to show you how the classifier works. So map classify is the package from PySal. You use quantiles, you pass in the attribute and ask for 5. It'll give you the breaks and whether you have open or closed intervals and the counts. So quintiles, we should have roughly the same number in each class. We could change the classes. So now we have deciles. If you change K, the number of classes, to 10, you get 10. I'll save that in an object. There's some attributes on the classifier object. You can format, you can get the bins. So for example, the bins are the cutoffs for the lower and upper bounds. You can get the counts if you need them. And then there's other classifiers in the library. So Fisher-Jenks is an optimal classifier. It uses a dynamic programming approach. If you want 10 classes, what it tries to do is define the breaks such that the variance within a given class is as small as possible, but the variance between the classes is as large as possible. It takes a while because it is a dynamic programming thing on a large number of polygons. And so it'll give you different breaks and therefore probably different counts depending on the statistical distribution. But it will always do best. So this is a measure of fit, and it's smaller is better. So it'll always dominate quintiles if that's what's important to you, fit. You can also use user-defined bins. So let's say I wanted to impose the class breaks. So I wanted 100,000, 500,000, a million, and 1.5 million. You can do that. Okay. And then geopandas uses all these. So you can feed them into geopandas and do nicer looking, more refined maps. So we're back to using geopandas. Here we're changing the classifier. That was quintiles. This is Fisher-Jenks. So you'll get a different depiction of the spatial distribution because we're using the hue for the value, but then where the high value polygons are, where the low value polygons are, that's a function of the spatial distribution. We could also change the color ramp. So I changed it to blues here, and you get a different visualization. The distribution hasn't changed, but the way we're symbolizing it and representing it changes.
Serge, you.
Yeah.
This again is the median home value is again an existing column in your data set, right? It's still not doing anything spatial to that, or is it?
No, you're exactly right.
Okay, yeah. So the Fisher-Jenkins is just a statistical model that it's applying on that particular column.
Right. It's basically a histogram, if you will, right? And now we're plotting the bin numbers.
Correct. Okay. But you're doing the plotting in a geospatial context. That's the yes.
Yes. Yeah.
Got it.
Yep. All right. Yeah. Okay. So that's another. Let's see. Same thing. All right. This is just more, I'm going to pull these out. This is doing it by county. If you wanted to loop over, do a different analysis for each county. This is breaking a simple for loop to do this for each of the counties if you wanted to break out each county individually. But it's reclassifying just on that subset of data. So the bins are going to be different. If there's variation in housing values across the counties, which there is. All right. Because the visualization ecosystem in Python is really amazing and fantastic and growing very quickly. There's really nice libraries we can use for interactive geovisualization. So we're going to look at GeoViews and same data. We're going to start with a built-in data set to see what GeoViews allows us to do. This is the natural earth data set that comes built into geopandas, but the idea is you can have interact with the view, pop-ups for the values, but I want to get back to our data. So we'll pull in, reread the data, and do a plot with this new library here. So the view doesn't know that it's geospatial data, so the aspect ratio gets wonky and things get stretched out. But if you pass in geo equal true, it knows that those coordinates are geospatial coordinates, and we'll get a more appropriate looking plot. So now things are referenced as you would be familiar with if you were familiar with Southern California. This is a little wrapper function, so we can do choropleth maps with GeoViews, and we'll see in a moment why that's very useful once we plot them. So now you have access to, I'm driving my mouse over it. You have pop-ups, which are very useful because the problem with choropleths, if your bins are not too thick, if your bins are wide, then two polygons that are in the same bin might have very different values, and you can't discern that from the colors. But with this additional type of visualization, you can use a pop-up to compare, say, these two out here in the East Coast, in the eastern part of the data set. We're in the first quintile, but these have different median values. So that's useful, but then you also have, you can zoom with the, scrolling my mouse, pan, and I can never remember the key binding to do the panning. And most importantly, reset. So that's GeoViews that we're able just to plug in the geopandas plotting together with matplotlib for the views. All right, and I think this one pulls in new tiles.
It's pulling data from somewhere, or?
Pulling the tiles in, yeah, and also depending on the complexity of the polygons, how many vertices there are, it can be slow.
And it's using bouquet underneath, or is?
I think GeoViews uses bouquet underneath, yeah, because this is the familiar bouquet interactivity. Yeah. So this is bouquet, and then we went and got a new tile layer from Carto, which is a company that does web tiles, and they're down in here. All right, so that's quick visualization. We're going to come back and use visualization when we start to do some analysis in the next notebook.
So, sorry, another quick question from the.
Yeah.
So if I look at the code that's there to do these visualizations, even though it's a few functions that are being put together, there are a lot of pieces, moving parts, right? So there's like hollow views, there's GeoViews, there's SciPy.
Yeah.
So what's your default mode of what's your advice to someone who's going to play as a student playing around with this stuff? Should they sort of use these notebooks as a jump off point and then modify? Is that what you would recommend?
Definitely, yeah, that would be the way to go because it is moving really fast.
Yeah. Okay. Yeah. Thanks.
All right. Spatial. Sorry, 0, 2. We're going into spatial weights now. close this. All right, so spatial weights. In our case, we have these census tracts, which we're interested in, and we want to come up with a way to represent whether two census tracts should be considered as neighbors. And neighbors is a general concept. So it could be neighbors because they share a border. It could be neighbors because they're within a certain distance of each other. Say their centroids are within 10 kilometers of each other. But it could also be more general distance, like socioeconomic distance. I want to say that two tracts that have similar ethnic distributions or compositions should be considered neighbors for statistical analysis. And the way that's encoded is with what's known as a spatial weights matrix. So if we have 1,000 polygons, this matrix conceptually is 1,000 by 1,000 matrix. And each value in the matrix tells us to what extent are polygon I and J neighbors. So this is the job of the weights. We're not going to store the whole weights matrix because many of them are sparse, but that's the conceptually the way to think about it. And this was where the library actually began, coming up with efficient ways to build these adjacency structures because they're widely used in spatial analysis. So we spent a huge amount of time and years on trying to optimize this so it could scale up to large problems, but also be fast and importantly support interoperability with R. And there's a pretty rich R ecosystem for spatial methods, and we interface with them as well as and Stata in the social sciences. And that's all part of libpysal, which is the lib part of the library. So there's a weights submodule in libpysal, and we're going to import some of these classes that build the spatial weights structures for us. And from splot, which is the plotting part of pysal, which tries to make it easy to do plotting. And Prabhu's question about the code for the previous notebook is true. That's sort of showing you how to construct this, but typically you do the same thing again and again. So we put the common use cases in splot. So different weights types. There's simple contiguity weights where we're going to say two polygons are neighbors if they share at least one vertex. Right? So queen weights, it comes from think about a chessboard and the moves that a queen can make. Queens can go diagonal or orthogonal, north, south, east, west. So if two polygons can be reached vis-a-vis each other by moving a queen, then they're considered queen neighbors. Right? And then we would encode the AB element of the weights as a 1, and it's a symmetric notion, so BA would also be a 1. So we're going to read in the geopackage again, same geopackage, and we're going to change the coordinate to UTM, which is it takes longitude and latitude, and we're going to convert it to meters. So universal trans Mercator. And we know, I know we're in zone 11 north. So this changes what the values are in the geometry. Now queen comes from libpysal, and it takes a data frame, and what it's going to do is determine which pairs of polygons are queen neighbors. So it examines in an efficient way which polygons share at least one vertex of their polygon chains. Okay, and it'll throw some warnings. Says there's one island, meaning it's a disconnected polygon. It is a polygon that shares no vertices with anybody else. That's one of the warnings. It also tells us there's 3 disconnected components, meaning you have groups of polygons that are neighbors of each other, but you cannot, they do not have a neighbor in the other component. And that can be important for certain types of analysis.
A quick question, Serge. Shashidhar is asking, is there any reference to the numbers used in the 2CRS function, as in these numbers? How does it? Yeah.
Yes. So this comes from the European Petroleum Survey Group. So the companies that are responsible for basically raping the planet and getting oil out of the ground, through history, they've developed these these references. So I think there's a quick website I can show you. Yeah, so if you actually type EPSG in a number, so I've done this many, many times, it'll take you to the website. And it gives you a little bit more information about what those codes mean. And sometimes when a researcher might send you a data set, you open it up in geopandas and all you have is this number. And nobody, at least sane people, don't know what these numbers mean. They don't know that, oh, that's WGS 484. So you look it up and you go to the website to look it up. Okay. All right. So we have our queen object. It's a contiguity queen. And our weights have a bunch of attributes. So the first thing we can do is find out for polygon 155, wherever that is in the data frame, I want to know who its neighbors are and what the weights are. So the neighbors, this is all stored in a dictionary, a Python dictionary under the hood. So polygon 155 has a neighbor with ID 4528. The weight is a 1. It has a neighbor 547. The weight is a 1. So this polygon has 4 neighbors. They all have a weight of 1. We can add 155 back in and say, well, this is the set, including the focal unit of the connected neighbors to 155. And we don't know who those are, but we can question the data frame and say, okay, that's great. Polygon 155, I don't know what that is. Well, we can query the data frame and we know that it's GeoID this. So we could look it up on the map and we have the attribute data for those neighbors, as well as the focal unit. All right. So these, if you consider the polygons, if you're using contiguity to define neighbors, your matrix, if you had it, was going to be very sparse because the counties in San Diego are by definition not going to touch, sorry, the census tracts in San Diego are not going to touch anything in Los Angeles because Orange County separates those two counties. And so there's a lot of zeros in the matrix and we don't store that. But if you wanted the full matrix, you can get it. So it's a big matrix, mostly filled with zeros because a lot of the counties are not going to touch each other. We can find out the number of neighbors for each of the tracks. So polygon 155 has 4 neighbors, but there's also an attribute called cardinalities that stores that for everybody. So you know the adjacency cardinality, if you will, for each polygon. How many neighbors does each polygon have? Now the weights are going to be useful when we do some statistical analysis in a little bit. We can transform them. So right now it's either a 1 or a 0 in the row of a weights matrix. We're going to want to do what's known as a row transform. So re-standardize the row by dividing by the sum of the row so that they're going to sum up to 1. And that's done with a transform property of the weight. And then if we extract the W again, now the row sums are all going to be 1 because we standardized it. The weights matrices are very sparse, and we use SciPy sparse to represent them under the hood. So they're very, very sparse, right? This is a fairly large matrix for the social scientists who work with spatial data, and there's very few non-zero elements. That percentage, less than 1% dense. All right. I'm going to plot the weights so conceptually you can get a better view of what's going on here. So this is what the weights are encoding. It's easier to see in the eastern part of the region. We're taking the centroid of each census tract and we're drawing an edge to its queen neighbors. All right, so it's a graph or a network based on the centroids, but the definition of the neighbor is whether they share an edge or not, share a vertex or not. And we can't see the graph here; it's too dense. But we'll extract it in a little bit. All right. This is the cardinality histogram. So the cardinalities tell us how many neighbors each polygon has according to this rule. And then we can plot the bin. So there are some census tracts that have very few neighbors, but there are a couple that have a huge number of neighbors, up to 20, close to 20 neighbors. And those are that's all the cardinalities, just for kicks. So that's queen. You could change the criterion and say rook. So now we're not going to include the diagonal moves. And rook means two polygons share an edge. They have to share an edge. It's not enough just to share a vertex. You have to share an edge. Similarly to what we did with the queen, you call rook from data frame and pass in the data frame. And the structure of the weights object is the same. But if we plot it, it's going to be less dense because rook is a more stringent definition for neighbors. And history.
Just a quick question
Yep.
on the plot. If you see the big center, there's a star-like
Here
thing in the middle, and there's one lonely node that doesn't seem to be a separate county. And
over
the one below that.
here.
Yes. So if you see on the that line.
Yeah.
It seems to go to something within this county.
Here.
Yeah.
Yeah.
So no. So the one that's the centroid of that county.
Tract, census tract.
Yes, and what's the one point in the middle which? No, not that one. The one to the bottom, a little bit lower. You see a black dot there. Yes.
This guy.
Yes.
Yeah. So this is another census tract down here. So this is the centroid of this big tract, and this is the centroid of this big tract. So they're neighbors because they share this edge, the white edge.
All right. Okay. Thanks.
All right. Okay. So in queen weights. One of the features of the library is the weights also support set theory operations. So differences, strict differences, intersections, unions if you want them. So the way a bishop would move is the diagonal movement. And the bishop, well, the queen is really rook plus bishop, right? So if we wanted to get the bishop, which we don't have in PySal, we would take the queen, but not rook, and that would give us bishop. If you want bishop diagonal neighbors, which it's pretty rare to want them, but sometimes in ecology and in hydrology with movements of like a river across, this can be important. I'm not a hydrologist, but I know people who are, and they use bishop weights in certain types of stream flow models, kinds of things. Not stream flow, drainage models or elevation type models, DEMs. So we can use difference. PySal's can take the difference between the queen and rook and give us the bishop weights, and that results in a lot of disconnected components, and we'll plot it and see why in a second. So we're going to plot the bishop weights. And so when you have bishop weights, which would be the ones that only one vertex, you get a lot of isolates who are not connected. All right, so those are contiguity weights. How are we doing for time, Prabhu?
5 minutes.
Okay, we're doing just about perfect. The other ways to do define neighbors is based on distance relationships. And this is where the coordinates become important, because you have to measure distance on the right metric, right? If you're using spherical coordinates versus planar coordinates, you need to know which one's relevant. And this is encoded by the CRS. So that code for this one is 26911. You could look that up on that website, or you can ask geopandas to spit out what it knows about it. Right. So these are in meters. So it's projecting from the sphere to two-dimensional space in a plane. So we could say, all right, I want to define neighbors as any pair of polygons whose centroids are within 2,000 meters of one another. And so in PySal, we have a distance band class that takes a data frame as an argument, and you give it the distance threshold. And there's a lot of polygons that are not within 2,000 meters of their nearest neighbor. And then we can plot that W. Okay. So what's that going to do? It's going to keep as isolates the ones that are in very far away, more than 2,000 meters away from their nearest neighbor. But you'll see edges connecting small census tracts that are close to other small census tracts. All right. So that's one distance type weights. Others are nearest neighbor weights. So you could say, I want everybody to have, say, 8 neighbors, KNN weights. Here, you have to be careful because if the coordinates are in lat long, those are spherical coordinates. So to specify that the correct way, this first way is the wrong way, where you pass in the data frame and you say, I want 8 nearest neighbors for everybody. That's ignoring the fact that they're decimal degrees for the coordinates, but it'll still calculate them as Euclidean distances and tell you these are neighbors. The correct way would be to pass in a radius argument and use either kilometers or miles. So that's the correct way. And it can matter. So even this matters at a global scale for sure. As your spatial extent of your study area gets bigger and bigger, curvature of the Earth comes into play. But even at this scale, Southern California, it can mess things up. So who's a neighbor for polygon 1487? You can get different results if you don't take the curvature of the Earth into account. All right, so there's a second type of distance weights, and then there's kernel weights I'm going to skip over. They're, rather than saying I and j are neighbors, put a 1 there. Kernel weights allow us to have a continuous value for the weight based on how far away the neighbors are actually. So rather than having a binary weights value, you now have a continuous value where the higher value means it's closer. So you use a kernel function, whether it's a triangle, a Gaussian, the usual suspects, we all support them. Maybe I'll do a quick one. Yeah, I'll do a quick one. So these are the kernel, these are neighbors, so it doesn't look any difference, but the value of the weights is going to be different. Right. And then I'm going to skip over the block weights because they're not used that often because I want to get to some more of the analysis. All right. All right, we'll do it. We'll use the weights for an interesting problem. This was an optional one, but it's sort of a cool problem. So we want to find the largest discrepancy in housing values between neighboring census tracts. So this would be a problem because we have a large number of census tracts in this data set. And what we want to do is find the pairs of tracts that are neighbors but have the largest gap in their housing values. That's what we're going to try and do. And this is motivated by a really interesting blog post. Oops. What did I mess up here? There we go. That I linked to here. So I put the URL. There was a blog post that was asking the same question, but for neighboring polygons where the life expectancy between the two polygons was as large, the discrepancy in life expectancy was as large as possible. Turns out it's very similar to where the housing values gap is large. Here we're using this, what we've covered thus far. We're going to use the Queen definition for neighbors for the county, for the census tracts in Southern California. And we're going to focus on housing values. So what we want to do is find the maximum pairwise difference, and that's NumPy. So we get the leverage NumPy. I want to get the full W matrix because this is going to make life easier. So PWDiff is a big matrix that has the difference in housing value between tract I and tract J, pairwise difference, an absolute value. So what I care about is the largest difference between my census tract and my neighboring census tract, which is the largest. And we're going to take that big matrix and multiply it against the binary contiguity matrix. And we're going to plot this soon, so hopefully it'll make more sense. I'm going to skip over that stuff and do the plot. Using Folium. Okay. Folium's another plotting library for maps that lets us do interactivity, and it's slow to draw. So this is going to take a little bit of time, but it'll allow us to interact with the map once it gets drawn. It's kind of convoluted because you have to write a data frame out to a JSON file, read it back in, and do the plot. So this is a quick map that's showing us where the biggest discrepancies are between neighboring polygons. And then once we plot this, we'll be able to interact with it. Here we go. Okay. Whoops. I scrolled down too much. This is kind of hard to do. All right, let's zoom in here. Okay, so this is where these are two contiguous census tracts. And the median housing value in this census tract is $83,000. And then across the street, so there's a street here, the median housing value in this census tract is over $1 million. Okay, so same street, different sides of the street, 83,000 versus $1 million. Okay, and this is in LA, so this is Wilshire Boulevard, for those of you who maybe know LA, and Westlake. But what this exercise is doing is finding those pairs where there's the largest discrepancy in neighboring housing values. So that was one of the pairs. There's some other ones up here. We zoom in. Yeah, it'll tell us. This one was $1 million, and then its neighbors was smaller. Its neighbor is this one up here. So this is a good example of the bishop. Well, almost the bishop, because these guys, whoops. This is a neighbor of this because there's a tiny little connection here. And so this one is the $1 million homes. This one, 220,000. So that's one use of the weights. Last one I wanted to get to today is the spatial autocorrelation. So this is testing for spatial clustering on the map. This is one of the most commonly used methods of exploratory spatial data analysis. And we have a library, part of the library called ESDA for exploratory spatial data analysis. The other packages we've seen thus far. We're going to use Seaborn for some of the plotting. And here we're using a different data set. We're going to zoom in on San Diego County, and it's from the United States Census, but it's annual data, so it comes from the American Community Survey. We're going to use the census tracts from the SCAG data, and we're going to plot housing values just for San Diego, where I'm at. Okay, so it's a little blurry because that's the resolution of the underlying tile that we got. So the city of San Diego is here. La Jolla is up here. I'm out here in East County. This is all desert. Most of the population is in basically west of about where my mouse is going. These are housing values. This is the histogram of housing values. So there are some census tracts where the median price is over $1 million. So this is millions, right? The median, or the mean, is about $400,000. And then we'll plot a different view of the data. So now darker hues are the census tracts that have the highest housing values. So obviously getting close to the coast matters, but whether you're close to the city turns out to be an interesting question. Depends on what side of the city you are on, whether you're in the north or the south. And then inland, you can have pockets of very high housing values. So what we want to do is look at this map and ask, is the distribution of housing values random in space or not? Now that's a really tricky question, because a simple way to ask is, are the dark polygons randomly distributed on the map, or are they co-located? And are the light polygons randomly distributed across the map, or are they co-located? It's complicated because these polygons are all different sizes and all different shapes. And our eyes are drawn to the large polygons, but statistically speaking, each polygon counts as one observation. So we have this challenge in geovisualization in that our brains are hardwired to be pattern detecting machines. We're really good at detecting patterns, potentially too good at detecting patterns, and we can fool ourselves. And we can definitely fool ourselves when we're looking at irregular polygons. And so we're going to use statistical methods, quantitative methods, to try and correct for that problem. The problem being that we're really good pattern detectors, but we can have too many false positives if we just rely on visual detection. And spatial autocorrelation are statistics that allow us to do that. They're going to combine two types of similarity. The first similarity we've talked about up to now, that is, are two polygons spatially similar in location? Are they contiguous? Are they within some distance cutoff? Yes or no, or we can make it a quantitative measurement of how neighborly they are. So that's what I mean by spatial similarity. Are two polygons close in space, geographic space? And we use the weights to handle that part of similarity. The other key part of similarity is attribute similarity. That is, the attribute you're interested in. Is it housing values, which it is in this case, but it could be disease rates, it could be rainfall, it could be crime rates, it could be innovation rates, could be school performance. There's thousands of attributes you could be interested in. So we want to know, are two polygons similar in their attribute values? Do two polygons have similar housing values, for example? And we're going to put these two notions of similarity together with what's known as the spatial lag. And the spatial lag is a weighted average. So the spatial lag for polygon I is a weighted average of the attribute values in its neighboring polygons. All right, so we're looking at housing values in a census tract. We know what the value is in tract I. We know the median value. We're going to ask, what's the average value in my neighborhood? And that tells me something about the spatial context. And it's really zipping together attribute similarity and spatial similarity. So the spatial lag uses the spatial weights to define the average value in the neighborhood. So let's create the spatial lag. There's a function in the weights module in PySal, lag spatial. It takes a spatial weight object and an attribute and constructs a new variable called the lag, and then we can plot the lag. So this is the spatial lag of the home value. That's the variable of interest. And for those of you who are remote sensors, this is a smoother, basically. It's smoothing the values. And what we're interested in is not the lags per se, but the lags in reference to the attributes. So we're going to plot them together. On the left are the original housing values by tract, median tract value. On the right is the spatial lag for the tracts. And what spatial autocorrelation does essentially is ask if these two maps are correlated. So we're essentially going to correlate this value with this value with this value, because this map is encapsulating spatial and attribute similarity. Okay. So the tests that do this for us are called global spatial autocorrelation tests. Global because they ask, is this map random or not? Yes or no. And there's a pretty large literature on this. The oldest approaches were based on what are known as join counts. So we're going to start with an artificial example and then come back to our map. Here, if we had this kind of map pattern where our polygons are squares and they're regular, this is a 9x9 lattice. For every pair of polygons that are neighbors, we can have three possibilities. We can have a black-black pair, meaning a black cell next to a black cell, white-white, or black-white, or white-black. That's what a join is, whether two polygons touch or join. And then we want to know what kind of join is it. Is it a black-black, white-white, or black-white? All right. So we're going to do this for our polygon data by making it binary, whether the census tract value is above or below the median, to sort of build up intuition. So now I've converted the map to tracts that have high housing values and tracts that have low housing values based on the median. And then we're going to use these join count statistics to test whether this is random or not, meaning are the black polygons located haphazardly on the map, or is there clustering? And so you could ask the same question of the white. So the join count module in the ESDA package in PySal takes the attribute and a weight and does the join counts. So it counts how many black-black joins there are on this map, how many times is there a black polygon touching a black polygon, how many white-white joins there are, and how many black-white joins there are. And those are the possibilities. That's all that can happen. There's only those three types of joins. But our statistic tells us, okay, you got 736. Is that larger or smaller than we would expect if the process that generated housing values was random in space? So we want to know, is this an extreme value or not? Is the map random or not? And PySal uses what's commonly used in the spatial statistics literature, permutations of the data. So we're going to create the null hypothesis. We're going to pick up the housing values off the map, shuffle them up, and reassign them randomly, because that is a random process, and recalculate our statistic, and do that, say, 10,000 times. And we're going to collect what happens when you do this randomly. We would expect to get this for the number of black-black joins, right? But what we got was way out here in the tail. The observed black-black joins was close to 750. When you do this randomly, you're below 500. So this is the null hypothesis, basically. If the null is true, this is what should happen. And the null is that the pattern's random. But this is what we got in our sample. way out here in the tail. So a pseudo p-value is simply the number that were as extreme as ours out of all the randomly values. So our pseudo p-value would be 1 in 1,000. So we would reject the null and conclude that the housing values are not random in that case. Okay.
Professor Serge,
you have a question.
Yep.
So Neeraj is asking, why do you call it a spatial autocorrelation and not just spatial correlation?
Great question. Thank you. I skipped over that. So if we go back to this map, it's called spatial autocorrelation. Let me answer that question first. Auto, because it's the same substantive variable, price, measured in different locations. So spatial autocorrelation. And the analogy is with time series autocorrelation. In time series autocorrelation, you have a time series for one variable, say rainfall or pollution levels. And when you're looking at time series autocorrelation, you're looking at the autocorrelation between the value in March and the value in February. But it's the same variable substantively, time series autocorrelation. And the same logic applies to why they call it spatial autocorrelation, because you're looking at the price here, lag, but now the spatial lag is more complex than the temporal lag, because in time, if you think about first order neighbors, you only have one first order neighbor, the previous period. But in space, you can have multiple first order neighbors, right? It's more complex, but the intuition is the same. Now, spatial correlation is when we're looking at the correlation between two maps of different variables, which is what we're really doing with the lag. Okay, so you can correlate spatial data. You can have a map of, say, pretend this wasn't the lag of housing values, but this could have been percent Hispanic, for example, and housing prices. And people do correlate those things. The problem is if either of those variables is spatially autocorrelated, your correlation coefficient can be meaningless, or not meaningless. Your inference about that correlation coefficient can be misleading, because the assumption with correlation is that the data represent a random sample. But if you have spatial autocorrelation, you don't have a random sample. You have dependence between your observations. So it's a complex topic, the notion, but it's called autocorrelation because it's the same substantive variable, and you're looking at the similarity of that value across similar nearby spatial locations. Hopefully that didn't confuse it. So the join counts, we threw away a lot of information. We went from a continuous variable to binary, but I think it's more intuitive to understand. If you had this many black cells, how many ways could you allocate them? And is this a rare allocation? And the answer we came up with is, yeah, this is really rare if it was randomly generated. So we can also do the continuous variable, same idea, but it's a different statistic. It's called Moran's I statistic. It's highly significant. So if we look at its p-value, it's also 1%. So even though we threw away a lot of information when we did the binary variable, it agrees with what you get when you use a continuous test, meaning you look at all the housing values, not just the high-low, but the whole distribution. This is Moran's I. Our value is way out here in the tail. This is what you would expect if the housing values are randomly generated. This plot over here on the right, this is called a Moran scatter plot. And the co-founder of the library, Luke Anslin, came up with this back in 1995, this device. And what it shows you on the x-axis is the standardized housing value in a Z transform, basically. So this is where the mean is. These are high values and low values for the housing values. On the y-axis, you do the same thing, but for the spatial lag. So then we have 4 quadrants up here. These are census tracts that are high value and surrounded by high value neighbors. In quadrant 1, quadrant 2, these are low value neighborhoods, but high value neighbors. All right, so sort of like a hole in the center of wealth. Down here, these are low, next to low, poverty clusters. And then over here, you have high values surrounded by low. And then this test is really what's the slope of this line, the Moran scatter plot, is actually the value of the statistic, the Moran's eye statistic. Okay, so if we have this sort of 45-degree angle, basically, there's a high, strong linear association between the value of a polygon's housing value and that of its neighbor. Right? If you know you have a high housing value, there's a higher probability your neighbors are going to also have high values. And if you have a low value, there's a high probability your neighbors also have a low value. All right. And then the last thing I wanted to cover, and leave some time for more questions or discussion, hopefully, are local autocorrelation statistics. They're called local because, in contrast to Moran's eye, or the joint count, which tell us something about the map as a collective, sort of the gestalt of the entire process, is the map random or not? That's a global statistic. The local ones allow us to detect hotspots and subsets of the observations that are maybe driving the overall pattern or depart from the overall pattern. Right? So these are called local autocorrelation statistics. And because we use random permutations for inference, I'm going to set the seed so we can get the same results if we rerun this. So the local measures are, we're now going to look at every point and ask, is this point representing significant local autocorrelation between that census tract and the group of its neighbors? That's what these local statistics do. So the local measures tell us which quadrant in the scatter plot is every location in. Are you up here? Are you over here, over here, over here? That's the first thing we get. Then we do conditional permutations and find out how many of the local statistics are significant, in the sense that their p-values, their pseudo p-values, are less than 5%. There's 241 of them. We can plot them and color them. So the red ones are significant local statistics, but they're different from the orange ones, which are also significant, but these are significant cold spots, poor census tracts surrounded by poor census tracts. These are significant hot spots, high housing value tracts surrounded by high housing value tracts. And these are significant outliers. In this case, the blue ones, these are low value tracts surrounded by high value neighbors. Right? These are important if you want to do real estate speculation. This is where you want to buy, because these are census tracts where the values are low, but the neighbors are high. So you might take advantage of, say, speculation. Not that I would do that, but okay. So then we can plot these and find out where they are spatially. So high are the significant markets that have high values surrounded by high values. They're non-random co-location. The blue are the poverty locations. So these are low housing values surrounded by low housing values. And you can see here down in South County, this is on the ocean. This is Coronado Island, basically, very expensive real estate. But there's a Navy base here, and then you get into where the Navy communities are, and largely large Mexican population, because this is Mexico right here in southern and the border. So this is large Hispanic population in the south. But this is not random. You see this clustering. And then in East County, this is a pocket of largely immigrant and Black neighborhoods here. All right. So this lets you to detect the cold and so-called hotspots. In this case, it's housing values, but you could do the same thing for any attribute that you have. And then splot, which is part of the visualization library, wraps this all up. So as Prabhu mentioned earlier, there's a lot of code to do a simple plot. And splot, which is now part of PySal, was a Google Summer of Code project by Stephanie Lemnitz, who's actually, I think, Ralph Gomer's sweetheart. I didn't know that until I met Ralph. Stephanie was a GSOC student with ours about 3 years ago, and she worked on splot and put this all together. So it gives you the scatter plot together with the cluster map and the original attribute. This is the original housing values. So you get a sense for how the spatial statistics are basically adding information to what can be really complex to visualize, the map itself. All right.
A couple of questions.
Sure.
So I noticed that you had something saying Lisa cluster. I mean,
yeah.
What does what does that stand for in this case?
So Lisa stands for, and Luke came up with this.
Okay.
Local Indicator of Spatial Association.
Okay.
That's what Lisa.
Okay, so it's a kind of plot that works for any kind of association you want to plot. Is that correct?
For local meaning the local spatial statistic.
Right.
Yeah.
Okay. The other question is, Sandeep is running into an error in the third notebook. He's getting a CSR error, invalid projection, no such column or something like that.
I'd have to see it.
Okay.
Yeah, that one might be tough to debug. If they send me a screenshot on an email, I can try and debug it with them.
Yeah, so we'll ask him to do that on the chat.
Okay.
Okay.
All right, I'm gonna have to change.
Yeah. So you can. Those are the two questions. So.
Okay. If there's no more questions, I can show you. I won't show you more notebooks. I'll just give you a better overview of what else is in the library that I didn't cover, if that's of interest, or maybe people are tired of hearing me talk. It's hard to tell because you can't see faces. So.
No, I think it's at least I've enjoyed. Because the notebooks you've done so far have covered a lot of.
Yeah, they do cover a lot. God.
Yeah.
Let me get to. I'll change real quick. And I'll put this link in. I'm just about done with a book I'm writing with two of the other PySal developers. That's under contract with CRC Press. Make this bigger. But that's available online.
Wow.
So they generally agreed to let us do this. So it's on geographic data science with PySal and the PyData stack. So Danny is at Liverpool and Levi is at Bristol. And you can go to this now. There'll be a dead tree version, but we're using JupyterBook, which is a fantastic tool. It's just made this so much better to work. But it covers much of what we did today, the choropleth mapping and the autocorrelation. But what we didn't cover today are things like point pattern analysis. So in the book, there's plenty of examples of dealing with points. We didn't cover inequality, which is the area I work in a lot. So there's a notebook on spatial inequality, clustering and regionalization, the more advanced stuff. When you want to do multivariate clustering with space, that's in there. Spatial regression, we didn't cover because we didn't have time, but there's that part of the library, and then spatial feature engineering. So machine learning with PySal, interfacing with scikit-learn and friends. So that is all this. We're due to finish a draft next month. We have all the chapters drafted, and some of them have been vetted already, but the book will be out mid next year, but it's available online right now if people want to explore it. And there's a binder to run the notebooks.
Yeah, so there,
Could,
can you share the link of this one? I can post it.
Yeah, let me get the...
It's a bit small.
Yeah, let me jump back to the... I'll put it in the backstage thing.
Oh yeah, sure. I'll share it with the stage.
Yeah.
Yeah, just did that. Thank you.
Okay, great.
So there are some questions. Do you want to take them?
Sure.
Or yeah, okay. So there's some comments that many folks enjoyed it. The first question that is not yet answered is what different clustering, Paritosh is asking, what different clustering algorithms can we use for spatial clustering?
Okay, so for spatial clustering, it depends on the type of spatial data. So whether you have polygons or points is a key, or networks, because you might want to cluster segments on the network. But typically it comes down to whether you have points or polygons, and they're different methods. And we've been looking at polygons pretty much in this workshop. And there you use, you can use traditional multivariate clustering like k-means or agglomerative clustering, but a lot of times that ignores space. So in PySal, there's a module called spopt, which does spatially constrained clustering. And that's in the book. There's a chapter in the book that explains in more detail this difference between aspatial clustering, like k-means or agglomerative clustering or partitive clustering, and then k-means with spatial constraints, meaning you're only going to group together observations that are geographical neighbors or neighbors of neighbors and are similar in attribute space. So for polygon data, that's the kind of methods that are used. For point data, it's all kinds of things like dbScan. There's these things called K functions that are used to identify clusters of points, but it's a different group of literature. Did I lose connection?
Yeah, I don't know. I sort of paused for a second. Yeah. So.
Yeah, it's starting to cyborg the sound.
Okay. Yeah. So there are no more questions right now. I'll share them with you if anyone asks.
Yeah, I think it's breaking up. All right. Okay.
We can hear you.
Okay.
Yeah.
Sorry.
Yeah, that's fine.
Yeah, I didn't hear the last question.
Oh no, I said there were no more questions.
Okay.
As far as I can tell. And we've told all the participants that they can ask questions on the chat room. So yeah, maybe tomorrow morning your time, if you could.
Yeah.
answer
Definitely.
if some.
Yeah, happy to talk to anybody or email.
Okay.
Great. Thanks everybody for your attention.
Yeah. No problem. And if you go to the stage chat room, you'll actually see everyone saying nice things
okay.
about.
Yeah.
If you on the same. Oops. I think he dropped out. I don't know how that happened. Just
yes, so he left it. He left the call actually.
okay. Maybe
So
he'll
yeah,
come back.
yeah. So if he is willing to chat with anyone, then maybe he can move into any of the launches. We have like 6 launch available, so he can move into any launch and interact with the attendees, if that's okay with him.